Hello students, welcome to EPG Parshala. In this session, we shall discuss the topic coupled ocean atmospheric system and El-Nino southern oscillation. At the end of the presentation, you will be able to answer the following questions. What is a coupled ocean atmosphere system? What is the mechanism of development of El-Nino and La Niña? How to monitor El-Nino southern oscillation events? And what are the effects of El-Nino and La Niña on Indian monsoon? The notion that drought in India, Indonesia and Philippines could be caused by the same condition that produced torrential rains in the United States, Peru and Chile might appear to the casual observer to defy logic. But in fact, that is exactly what can happen during the extraordinary change of events known as El-Nino. In the recent years, El-Nino events have become the focus of intense discussion and not only among the scientific community, but also within the ranks of the media and the general public as well. However, the conditions that give rise to these events have been well observed before a century. El-Nino and La Niña are the large-scale coupled ocean atmospheric phenomena linked to a periodic warming and cooling in the sea surface across the central and east central region of equatorial Pacific. The genesis behind their formation is very complicated. They are important because of their global impact. Global impact in the sense they cause drought, flood, increased precipitation, hurricanes or wildfires around different corners of the globe. They have also direct impact on the global food market or global economy. The Indian monsoon rainfall is highly linked with the global meteorological situations which are technically called as southern oscillations. Together, El-Nino and southern oscillation are known popularly as ENSO. Now let me explain some of the technical terms that I shall be frequently using during this discussion. Climatology. It is a quantitative description of values of a climatic variable averaged over a period of time. For example, the case of rainfall has been given here. From this figure, we can say that the rainfall over most locations of the oceans are in general higher than the land masses. Convection. It is a mass motion in a field resulting in transport and mixing of the field. More specifically, it refers to motion associated with a rising current of air. Then equatorial upwelling. It is the upward motion of subsurface water toward the surface of the ocean. This is often a source of cold and nutrient-rich water. Strong upwelling occurs along the equator where easterly winds are present. Thermocline. This is a thin but distinct layer in a large body of fluid like ocean or lake. So in this layer, temperature changes more rapidly with depth than it does in the layers above or below. It forms when water at the surface of an ocean or lake is heated up while the water below that layer stays cool. Now trade winds or equatorial easterlies. Trade winds blow from the subtropical highs about 30° latitude or also called horse latitudes. So these winds blow from this subtropical highs towards the low pressure region of the equator. They are named from their ability to quickly propel trading ships across the ocean. In northern hemisphere, trade winds are northeasterly and in southern hemisphere, trade winds are southeasterly. Teleconnections. Climate anomalies being strongly and statistically related to each other at large distances, typically thousands of kilometers. Take for example, linkage of sea level pressure at Tahiti in the Pacific Ocean and Darwin Port of Australia. This defines the southern oscillation. Now tropical Pacific. When we mention of tropical Pacific in the ENSO context, we are talking about the region marked by red in this figure. In the western part of the tropical Pacific, there is countries like Indonesia, Philippines and Australia, whereas in the eastern part, there are countries of Central and South America. El-Nino and southern oscillation. It is the largest interannual climatic variation. It involves an interaction between the tropical Pacific Ocean and the atmosphere above it. Its impacts are felt worldwide. Heart of the ENSO lies in the tropical Pacific Ocean along the equator. Changes in SST, that is sea surface temperature, ocean subsurface temperature, rainfall and winds contribute to produce the ENSO cycle. The variations in the Pacific basin within about 10 to 15° latitude of the equator are the primary variables driving this ENSO process. In the few subsequent slides, we shall discuss the coupled ocean atmospheric system. Ocean atmospheric coupling. The oceans and atmosphere are the two large reservoirs of water in the Earth's hydrological cycle. The two systems are complexly linked to one another and are responsible for Earth's weather and climate. Oceans helps to regulate temperature in the lower part of the atmosphere, while the atmosphere in large part responsible for the circulation of ocean waters through waves and currents. Now let me tell you the theory behind the ocean atmosphere coupling. A large scale anomaly of sea surface temperature induces diabatic heating or cooling of the atmosphere, which changes atmospheric circulation and hence the wind stress and heat fluxes at the ocean surface. As a result, ocean thermal structure and circulation gets modified, giving rise to a series of positive feedbacks that strengthen the initial SST anomaly. Ocean and atmospheric circulations are interdependent on each other, and the SST serves as a link combining these two elements. The strength of ocean atmospheric coupling varies from region to region. In the tropics, the coupling is very strong because tropical wind stress is largely controlled by sea surface temperature, whereas in middle latitudes atmospheric circulation depends on local SSTs and the dependence is weaker. So, El-Nino is the warm phase of a natural oscillation driven by tropical ocean atmospheric coupling, and perhaps this is the most striking example of active coupling. Heat exchange between ocean and atmosphere is a product of a number of processes such as solar radiation hits the ocean, then ocean radiates back long wave radiation. This process cools the ocean. Then heat is transferred from the ocean to the atmosphere by way of conduction and convection. Also there is evaporation from the ocean surface, and this evaporation process cools the ocean. In the few subsequent slides, we shall elaborately discuss about El-Nino and La Niña. This table gives a brief definition of El-Nino and La Niña. El-Nino and La Niña are Spanish words. El-Nino means the Christ child, which appears in the Christmas, and La Niña is the girl child. In case of El-Nino, there is periodic warming in the sea surface temperature across the central and east central equatorial Pacific. In case of La Niña, instead of warming, there is a periodic cooling in the same region. El-Nino occurs every 3 to 5 years and lasts about 1 year, whereas La Niña appear every 4 to 5 years and last for 1 to 2 years. Now the mechanism and development of El-Nino and La Niña. First, let us see how pressure plays a role in it. In case of normal year, there is a low pressure over Western Pacific region and high pressure over Eastern Pacific region, that is South American region. In case of La Niña, this pressure changes, and this is called southern oscillation. That is, during a El-Nino year, you will find higher pressure over Western Pacific region and lower pressure over South American region. In case of La Niña year, it will be normal year, but the magnitude will be higher. That is, the air pressure over the Western Pacific will be lower than its normal, and the pressure over the South America will be higher than the normal value. Then flow of trade wind. In normal year, trade winds blow from east to west in the equatorial Pacific region. That is, the wind blows from South American side to the Indian Ocean sides, and along the wind the ocean water also moves towards the Western Pacific region. That is why in a normal year you will find a higher sea level in the Western Pacific region than that of Eastern Pacific region. During a El-Nino year, trade winds either weaken or blow from west to east. In case of La Niña year, the winds are easterly only, but the magnitude or strength is higher. Now, position of thermocline. In a normal year, there exists a shallow thermocline along South America coast and deeper thermocline near the Western Pacific region. In a El-Nino year, the thermocline in the South American side gets deeper and the Western Pacific side gets shallower. In case of La Niña year, the thermocline along the South America will be shallower and thermocline near Western Pacific is deeper than the normal years. Now, upwelling. In a normal year, there is a lots of upwelling, that is moving of cold water from the underneath of the ocean to the surface, and this upwelling happens off the coast of South America, that is the Eastern Pacific region. In case of El-Nino year, there will be either little upwelling or no upwelling, and the water at the ocean surface will be warmer. For a La Nina year, the upwelling of the Peru coast or the eastern Pacific region will be more than the normal, and this upwelling brings cold nutrient rich water to the surface. Now let us see what role temperature plays in this El-Nino and La Nina development. In normal year, warm ocean water, clouds and moisture are pushed away from North American side. In El-Nino year, western Pacific Ocean is colder and eastern Pacific near the coast of South America remains warmer. Warm surface water slows back along the equatorial Pacific. In a La Nina year, western Pacific Ocean remains warmer, whereas the eastern Pacific near the coast of South America is colder. Warm ocean waters, clouds and moisture are pushed away from the North American side. This figure shows the wind circulation pattern both at the surface level and at higher altitude during normal El-Nino and La Nina years. And this is in the atmosphere over tropical Pacific and the region bounded by 120 degree east longitude and 80 degree west longitude. The associated changes in ocean current, then shape of the thermocline and zones of strong convective precipitations are also depicted here. Like in a normal condition, in a normal year, the convective precipitations are generally in the western Pacific region. In a La Nina years, that shifts far of the western Pacific, and in case of El-Nino year, either it is in the central Pacific region or towards the eastern Pacific region. Upwelling, sea surface temperature and flow of water during normal El-Nino and La Nina condition. These figures have been taken from the reports of Tropical Ocean Atmospheric Project. During a normal year, the surface height is more in the western Pacific, sea surface temperature is higher and there is upwelling of cold water near the South American coast, that is in the eastern Pacific region. During El-Nino year, overall tropical Pacific is warmer, sea level and temperature is higher in the eastern Pacific region and there is no upwelling. During a La Nina year, overall the ocean is cooler than normal, western Pacific is warmer and there is a huge upwelling of the Peru coast, that is a huge upwelling in the eastern Pacific region. Let us look at the reason why does El-Nino and La Nina occur. Exact reason for why does they occur is still not understood. El-Nino results from interaction between the surface layers of the ocean and the overlying atmosphere in the tropical Pacific region. It is the internal dynamics of the coupled ocean atmosphere system that determine the onset and termination of El-Nino. The physical processes are complicated, but they involve unstable air-sea interaction and planetary scale oceanic wave. The system oscillates between warm phase, that is El-Nino phase, to neutral or cold phase, that is La Nina phase, with a natural periodicity of roughly about 3 to 4 years. External forcing from volcanic eruptions have no connections with El-Nino. Also, sunspots, as far as we know, there is no role of sunspots in bringing El-Nino or La Nina. In the next slide, we shall discuss how ENSO, that is El-Nino and Southern Oscillation events, are monitored. These El-Nino and La Nina events are monitored with the help of some indices. These are like Niño 1+2, Niño 3, Niño 3.4 and Niño 4. Like in case of Niño 1+2, this region typically warms first when an El-Nino event develops, and the observations are taken between 0 to 10 degree south latitude and between 80 to 90 degree west longitude region. Niño 3, the region of the tropical Pacific that has the highest variability in sea surface temperature on El-Nino time scales. The observations are taken between 5 degree south latitude to 5 degree north latitude and between 150 degree west to 90 degree west latitude. Niño 3.4, for this index, the region defined is 5 degree south to 5 degree north latitude and 170 degree west to 120 degree west longitude. This region is typically located in the far off western Pacific. The Niño 4, here the region defined is 5 degree south to 5 degree north latitude and as per longitude 160 degree to 150 degree west longitude. This is the region where changes of sea surface temperature lead to values around 27.5 degree centigrade, and which is thought to be an important threshold in producing rainfall. Now let us look how El-Nino and La Nina events affects the Indian monsoon. Sir Gilbert Walker inferred that quantity of rainfall in the Indian subcontinent was often negligible in the years of high pressure at Darwin and corresponding low pressure at Tahiti. Conversely, low pressure at Darwin bode well for the precipitation quantity in India. Thus, he established the relationship of southern oscillation with quantities of monsoon rains in India. The ENSO is known to have a pronounced effect on the strength of southwest monsoon over India, with the monsoon being weak during the El-Nino years. On the converse, La Niña years had particularly good monsoon strength over India. Kumar et al. Reported years with moderate to extremely cold state, that is, when Nino 3 index is less than -1, have had abundant monsoon rains in India without exception. On the other hand, years of moderate to extremely warm states, that is, when Nino 3 index value is higher than -1, those years have not been really reliably dry. The 6 leading droughts since 1871 have occurred along with a standardized Nino 3 index value higher than +1. But the presence of El-Nino has not guaranteed drought in India. In fact, there is no simple association that describes the relation between the Indian monsoon and Nino 3 sea surface temperatures when moderate to strong El-Nino conditions exist. This figure is a plot of all India area weighted mean summer monsoon rainfall published by IITM Pune. The long time series of this index since 1871 have revealed several interesting aspects of the interannual and decadal scale variations in the monsoon, as well as its regional and global teleconnections. It is interesting to note that there have been alternating periods extending to 3 to 4 decades with less and more frequent weak monsoons over India. For example, the 44-year period between 1921 and 1964 witnessed just 3 drought years. During such epochs, the monsoon was found to be less correlated with ENSO, whereas during the other period like 1965 to 87, it has only 10 drought years. The monsoon was found to be strongly linked with El-Nino and southern oscillation during this period. During the period 1871 to 2014, there were 19 major floods in India. Here, flood has been defined as rainfall anomaly exceeding +10%. Usually, La Niña years in India caused more than normal summer monsoon rainfall, but there are years like 1990 and 2000 when the amount of rainfall was scanty or at least less than the normal rainfall. During the period 1871 to 2014, there were 25 major drought years. Here, drought has been defined as when rainfall anomaly was -10% in terms of standard deviation. Usually, El-Nino years in India caused less than normal summer monsoon rainfall or drought-like situations, but there are years like 1900, 1944, 1976, 1997 and 2006 when the amount of rainfall was abundant or at least more than the normal rainfall. This table gives another statistics for the period 1880 to 2008. Out of this 128 years, 18 years were categorized as El-Nino years, of which 7 had received deficient rainfall. Then 86 years was categorized as normal rainfall years. 24 years were categorized as La Niña years, but only in 10 years rainfall was excess as per this index. To summarize, the coupling between ocean and atmosphere is straightforward. A large scale anomaly of SST induces diabatic heating or cooling of the atmosphere, which modifies atmospheric circulation as well as the wind stress and heat fluxes at the ocean surface. As a result, ocean thermal structure and circulation gets modified, giving rise to a series of positive feedbacks that strengthen the initial SST anomaly. El-Nino and La Niña both develop due to large scale interaction of ocean and atmosphere. SST and sea surface pressure are the main drivers of these processes. Both of them have significant impact on a global scale due to teleconnection. The impacts of El-Nino and La Niña are more devastating than the fortunate. El-Nino episode is characterized by deficient or less than normal rainfall in Indian subcontinent, while La Niña episode is characterized by more than normal rainfall in the Indian subcontinent. There is no simple association that describes the relation between Indian monsoon and Nino 3 sea surface temperatures when moderate to strong El-Nino conditions exist. Thank you.